Okay, so now we are ready to talk about gradient descent. So the idea is following. Suppose we want to minimize a nonlinear function like this. Okay, so you probably need a little bit imagination. But anyway, this function, this example here is you want to minimize x1, x0, x1. So it doesn't really matter how do we name these variables. X0 square plus x1 square. Okay. So somehow it looked like a ball, or BOWL. Okay, look like the ball having an upward curvature. So in that particular case, pretty much what we want to do is the following. We're going to start at whatever point we have. So this is an unconstrained problem, so we may start at any point. At any point, we would consider its gradient. Okay, so its gradient is something that we know how to calculate. The gradient is an n-dimensional vector. So this may sometimes be misunderstood. The gradient is some kind of partial derivatives. Okay, and in many cases, when you think about partial derivative, you may think about some kind of slope. All right, so that may be true when you are talking about a single dimensional problem. When you only have one decision variable, you may have that interpretation. But when you have multiple decision variables, okay, in an n-dimensional space, the gradient actually is a direction where if you move along that direction, then you may try to improve your current solution by moving along that direction. Okay, so later we will give you specific ideas about that. But for this one-dimensional problem, if at a point you talk about the gradient, that's pretty much whether you want to move to your left or to your right. All right? When you see the gradient is 3, for example, that means you want to move to your right because your gradient is positive. Or if you see -6, then you want to move to your left, something like that. So in a two-dimensional problem, if, for example, here, you see that your gradient, suppose, is this direction, okay? Then that means you want to move along that direction. Something we want to emphasize here. The gradient is a direction to move. It is not the slope. Okay? So we want to know whether the gradient gives us an improving direction. And here, improving means we want to minimize the function, right? So we want to improve by getting to a lower point. For a given function, whether it's one-dimensional or two-dimensional or whatever, at a point, we have the following proposition. For a twice differentiable function, its gradient is an increasing direction, okay? That means what? If you move along that direction, okay, so you are at x. You know x is a vector. It means some kind of locations, all right? So in a two-dimensional space, your x may be here. And you know you have a gradient. Gradient is another vector. Let's say your gradient is this direction, okay? Then if you move for a small step size, if you move by a small a, so your a may be small, like this. So this is your a gradient f, okay? So from x, you move along that direction with a small a. That means you will move to a not so far point. And for that point, you're going to see that it is greater than your original point. The functional value would be greater than the original point. So what does that mean? If you move along the gradient, so certainly we don't guarantee that you will keep improving forever. But if you don't move too far, for all those a that is small enough, you will see some improvements. Okay? So in a one-dimensional example, if you are here, then your gradient is going to tell you if you move along this direction, then you're going to get some improvements. If you are here, on the other hand, then your gradient again is going to be some positive value, definitely. And it guarantees you that if you move for a long distance, for a short distance, then you would see improvements. Okay, so it's not always true for a large A, but it must be true for local points for small a. So that's the idea for gradient. Well, this actually can be proved. So how to do that? Recall the following. We are having this particular thing. So if you consider this limit says that from x, I want to move along a direction d with a small step size. So my a goes to 0. So for this particular function, I'm talking about what's my resulting functional value and what's my initial functional value. So in a one-dimensional problem, okay, suppose it's like this. This is our f of x. This is our x. And then this would be our f of x on the red line segment. And then if I move for a little bit distance, x plus ad, then this would be my second functional value. Okay, so this is my second functional value. So their difference would be this one. The difference is going to decrease when you make a smaller. And when a really goes to 0, the 2 points would coincident with each other. And then that would give you the slope in some sense. Okay, so that means the left hand side is the slope for this particular function, f at the point a or at the point x. Okay, so if that's the case, then also we know one thing. We know that for calculus, from the calculus textbook, you have learned that this particular limit may be calculated as first you find a gradient, and the second you do one tiny step, the directional, this is called directional derivatives. Okay, pretty much you say, okay, this particular FFA thing is going to give you the gradient, and the direction that you want to move gives you this particular direction. So in that case, this is somehow says, oh, okay, so if I know at a point my gradient is here, and also I know I want to move along this particular direction, then that particular slope, that particular quantity would be determined by these two parts, the product. So what we have now is that, well, we have the following. This particular limit is going to be the gradient times the gradient. Okay, so if that's the case, then this is pretty much some kind of improving direction, because this is some kind of square, and that's going to be non-negative. Or if your gradient is not 0, then it is guaranteed to be positive. Okay, so don't forget that this particular this d vector is a vector. So here you should have a transpose. Okay, so your gradient is also a vector. Originally it's a column vector, so that's why you do a transpose to make it a row vector, and then a row vector may be multiplied with a column vector. So as long as your a is small enough, this is going to be greater than your original value. So this has been proved that the gradient gives you an improving direction. In fact, the gradient is giving you a fattest increasing direction. So at a point, if you want to move, if you want to increase as much as possible, moving along the gradient is at least a locally optimal strategy. Okay, so later, if we want to minimize our function, we will first find the gradient like this, and then we will move along the opposite direction. That's going to help us minimize ourselves as soon as possible.